All right, so welcome everyone to this week's IMP One World Mathematical Physics Seminar. For those of you who might be joining us for the first time, this is the regular seminar series of IMP, International Association of Mathematical Physics. And if you want to find out more about our organization, the seminar, and also join our mailing list, there is some more information in the chat together with the slides of today's talk. And this meeting, as all our meetings, is going to be recorded and you can watch it on our YouTube channel. But now let's go straight into the talk. It's my great pleasure to introduce Giovanni Felder from ETH Zurich, who is going to talk about Boltzmann's billiard and table tennis. Giovanni, take it from here. Thank you.
Thank you very much, Kasia. So today I'll talk about some discrete time dynamical systems. The first of which will be the model created by Ludwig Boltzmann. And so I will mostly speak about the billiard, and I will also explain some work in progress on the table tennis, which is a three-dimensional generalization. Okay, so I will start with telling you what this Boltzmann billiard is, and it turns out that this is similar to another, or is part of a family of systems which have the so-called Poncelet property. And so I will review the very classical construction of Poncelet. And after that, I will explain, and so all these models have to do with elliptic curves. So I will explain the relation of these models with elliptic curves, in particular the Boltzmann system. And for that, it's convenient to go to the complexification. Then I will go back to the real locus to understand the physical problem. And finally, I will tell you about this newer result on the three-dimensional case. Okay, so what is this system? So this system was invented by Ludwig Boltzmann in 1868. And so he considers a billiard, so a motion of a particle in a plane, which is subject, but with an external force, right? So it is subject to a central force. But on the billiard there is some boundary, so some line in this plane at which the particle gets reflected elastically. And so Boltzmann took as a potential a Newton potential and also a centrifugal force proportional to the inverse cube of the distance. So the potential would be lambda over r squared. So for instance, in the lambda equal to 0, we will mostly talk about the case lambda equal to 0, so just the pure gravitational force. The trajectory would look like this, right? So it will follow some Kepler trajectories for a while until it hits the wall. And when it hits the wall, it just jumps, so it's reflected elastically and follows another Kepler trajectory, and so on, right? Okay, so why did Boltzmann invent this system? So I think it is in the context of his ergodic hypothesis, right? So Boltzmann, as you know, formulated the claim or the hypothesis that if you have a kind of generic dynamical system, it will be ergodic. You can describe it by statistical, it's chaotic, and you can describe it by statistical mechanics. But of course, it's as you know, it's very difficult to create examples of such systems because all the systems that we know and we can solve because they are integrable, so they are far from chaotic. So, but then he wanted to propose a model which is presumably chaotic. So his proposal was to use this system here, and he claimed it should be, except for very special values of the parameters, it should be an ergodic system. And this claim is not complete. We will discuss this again. It is not completely true. And so let us discuss this system. So we have conservation laws, right? The energy is conserved because at each reflection, the energy is conserved. And now you can consider this as a discrete time dynamical system by considering the Poincaré map. So the Poincaré map would be the map between, you start from a position at a moment where the particle hits the wall, and you follow the particle until the next hit. So in this way you get some map on your phase space. So if you record position and momentum each time it hits the wall, you get a phase space and a map on this phase space, and your dynamical system is obtained by iterating this map. So you have a discrete time dynamical system. And so this, the phase space or the configuration space of this system would be the energy surface XR. I write this R because I will later complexify. So we have like two coordinates of position and two coordinates of the momenta, and you have two conditions. The energy is fixed to the value E, and the second coordinate, so we imagined our wall at, so the center of attraction is at the origin, and then the wall would be at x2 equal to h. The momentum will be positive, say at the moment where it's about to leave the wall. So we have this this space here, and on this space we have this Poincaré map, which is a map to the next, from one heating to the next heating. Okay, so what Boltzmann showed is that this preserved a natural area form. So it's an area preserving map. And so he proposed that this should be chaotic, and that his statistical description would be appropriate for such a system. Okay, so so what happened is that Giovanni Gallavotti a few years ago started to read those old papers, and he kind of reviewed them also from a historical perspective, and he started to do some numerical simulation in the case lambda equal to 0. So there is no centrifugal force, and you consider just the purely gravitational billiard. And so he noticed that actually this system is integrable. And so more precisely what he noticed is that if you follow the foci of those ellipses, right? So one focus is the origin, of course, and the second foci, he noticed that it moves on a circle, okay? So, and with Jauslin, he proved later that the second focus moves on a circle. So the radius of that circle is an integral of motion. Okay, so and the center of that circle is the reflected image of the origin with respect to the wall. So this is the picture that one has. And so now let me reformulate the theorem of Gallavotti and Jauslin in a more kind of classical mechanics framework. So recall that before putting this wall, we know that we have some conserved quantities of the Kepler problem, the very well-known conserved quantities. So we have the energy and the angular momentum, so which would be perpendicular to the plane of motion in this case. And then there is a so-called Laplace Runge length vector, which was actually, go back to Johann Bernoulli's student Hermann, which is also a conserved quantity. It's and it's this combination of angular momentum and position and momentum. And so we have like six, well, in the three-dimensional case, we would have seven integrals of motion, the components of the angular momentum, the components of the Laplace-Runge length vector, and the energy. But they obey relations. So the angular momentum is perpendicular to the Laplace vector, and you have this quadratic relation between the components. And right, so this is the very classical, before introducing this wall, it is a very classical picture for the Kepler problem. And geometrically, you can see those quantities in these Kepler trajectories, the conics. So for negative energy, you have ellipses, and one focus is in the origin, in the center of attraction. The semi-axes are given by the energy. So all this, if we fix the energy, all the major semi-axes are always the same. And then an interpretation of this Laplace vector is to, if you divide by mass times energy, is the vector which points at the second focus from the first focus. Okay, so this is the classical picture. Now, in a slightly more mechanical formulation, the theorem of Gallavotti-Jauslin can be formulated in the following way. So the Poincaré map of the Boltzmann system, Boltzmann billiard, with purely gravitational force and the wall at distance h to the center, preserves the energy, and this combination, so the absolute value, or the square of the norm of the angular momentum minus 2 times h times the perpendicular component of the Laplace-Runge length vector. So this would be the component of the length vector which is perpendicular to the wall. So this combination is, there is some relation between the radius that I was mentioning before, the radius of that circle on which the second focus moves, and this d and the energy. But so this is another possible formulation of the fact that we have an additional integral of motion. So now we have a discrete time dynamical system on each level set. So these are now one-dimensional level sets. The level sets of the energy were two-dimensional, and now we have a foliation by this second integral of motion. So at least for lambda equal to 0, without the centrifugal force, the system is integrable. And I will discuss later what to do with when you perturb it, but let's start to consider this thing here. So this is our discrete time dynamical system. So now, before discussing it further, because I would like to explain the Poncelet property of this system, I will first review what is a classical Poncelet problem. Okay. So the Poncelet theorem is the following one, 1822. So if you have a pair of conic sections, for instance, two circles or two ellipses, and for the sake of the argument, let's suppose that one is contained in the other, but this is kind of general. So if you have a pair of such conic sections which admits a polygon, which is inscribed in one and circumscribed about the other, then it admits infinitely many such polygons, all with the same number of sides, and each point of the first conic can serve as a vertex. So this is one picture of, so you have two ellipses, these blue ellipses, and then there is this kind of pink polygon, what is it, a pentagon, I guess, which is inscribed in the outer ellipse and circumscribed around the inner ellipse. And now you can move it around, and you always get such a closed polygon. And you can think of it as a dynamical system, right? Discrete time dynamical system. Namely, imagine that you start from a point on the boundary, on the outer ellipse, and then you follow a tangent to the inner ellipse until you hit the outer ellipse again, and then you continue like that. And then the question of existence of such polygons is whether whether this orbit is periodic, right? If you come back up at the starting point after, in this case, 5 such maps, then you have a periodic orbit. And then you can say that the Poncelet property is that if one orbit, if the two conics are positioned in such a way that that you have a periodic orbit, then all orbits are periodic with the same period. And right, so this is the classical Poncelet property, and it started, if you like, with the Euler, the so-called Euler triangle, which goes back before, it goes back to Chapel in 1746. It's the so-called Euler triangle formula, which in his case you consider two circles, and you ask for which position of the circles you have a triangle which is inscribed in the outer circle and circumscribed about the smaller circle. And so how to describe the position between these two circles? Well, you give the two radii, small r and capital R, and the distance between the two midpoints. And so the Euler triangle formula is this relation here between these quantities. And so I don't think this formula is in the writings of Euler. It is in some older paper of Chapel, who was writing on the, I don't know, Gentleman's Quarter or the Ladies' Magazine, and was writing such kind of mathematical riddles. And so this is, but then you have infinitely many such triangles, and you can take any point on the outer circle as a vertex of one of those triangles. It only depends on this D and R. And then later, Fuß, Steiner, and so there was a lot of activity to find a similar Euler formula for quadrangles, pentagons, and so on, and it went up to 8 sides. And then the theory of elliptic curves appeared, always by Jacobi, Abel, and so on. And so Jacobi understood that this is really a question of elliptic curves, right? Points of finite order on elliptic curves. And later, Cayley gave some kind of general formula generalizing this Euler triangle formula. Okay, so let me explain that, and I will give some kind of more modern formulation due to Griffiths-Harris. I think it's a clear way to understand what this story is. So suppose you have two conic sections. Imagine two circles in the plane. Then you consider this incidence variety. Namely, you consider the space of all pairs. So we have these two circles, C1, C2, and so P is a point on C1, and L is a line which goes through P and is tangent to C2. Okay, so this would be the incidence variable, right? It consists of points, pairs consisting of a point and a line. The line goes through the point is on the outer circle, say, and the line is tangent to the inner circle. Okay, and so on this space we have two involutions. Namely, we can change the point because the line will meet the circle C1 into 2 points. And so the first involution will map P to P prime, where P prime is the other intersection point of the tangent to the circle C1, let's say outer circle. And the second one, you keep the point and you take the other tangent. Through every point of this outer circle, there are exactly two tangents, or generically two tangents to the inner circle. Okay, now, but this is kind of can be formulated purely in terms of, I don't know, algebraic geometry, right? And you can complexify, you can go to the complex domain, and you can see that both have fixed points. So I don't know, intersection points between the circles, and so we have a space, a kind of complex variety with two involutions, which both have fixed points, and this will play a role later. And now, what is our dynamical system? Our dynamical system is the map of the dynamical system is a composition of these two involutions, right? So, and then if you start from a point on the outer circle, say x0, and then you do t of x0, t square of x0, and so on, and you get to the sides of a broken line which closes to an n-sided inscribed-circumscribed polygon if and only if the nth iteration is x0 is a fixed point for the nth iteration. So this is a way to formulate these things, to decompose the Poincaré map into two involutions. And so in papers of Griffiths and Griffiths-Harris, they observed that X, this space of pairs, maybe complexified if you want, is an elliptic curve, and thus it is biholomorphic to a group C modulo a lattice Z squared. And so now you can classify involutions in the. So involution is a map whose square is the identity. You can classify involutions of elliptic curves. So there are two types. There are those which are translations by a half of a lattice vectors. If you iterate it, you get the identity. And those have no fixed points. And then there are those with fixed points. And all the involutions, except the identity, which have fixed points, are necessarily of this form. Z goes to minus Z plus A. And the composition of two such involutions is a translation by an element of the elliptic curve. Okay, so this is kind of without calculation in some sense, except that you have to understand that it is an elliptic curve. You can deduce that you have this Poncelet property, because if your map is a translation of your elliptic curve, then either all orbits are periodic or no orbit is periodic. So this map T has a periodic orbit of period n, if and only if this A minus B, corresponding to the two involutions, has order n. It's an element of the group of order n. And in this case, all orbits are periodic, and the Poncelet theorem holds. Right. So this is some kind of modern formulation of the Poncelet theorem. It doesn't give you a formula for when you have periodic orbits, but at least you have this thing. And Cayley gave some very explicit construction of when an elliptic curve has, when an element of an elliptic curve has order n. Okay, so let's go back to the integrable Boltzmann system. What I would like to convey is that this Boltzmann system is basically the same story. The same arguments applies to this Boltzmann billiard. So let's try to imitate the construction. So first there is a simplification. We can choose units of measure so that we don't have this parameter mass and Newton constant, and h was the distance between the center and the wall. Let's set them all equal to 1. Then, okay, let's consider this incidence variety. Now, what is it? So we have P, a point on the wall of our billiard, and K is a Kepler conic, a trajectory, a Kepler trajectory, which goes through this point. And this is a union of such level sets for our two integrals of motion. Again, we have two involutions which preserve each level set. So one involution will map the pair pk to the map p prime k, where p prime is the other intersection point of k with the wall. So generically, if you intersect a conic with a line, you will have two intersection points. So this is the map which maps one intersection point to the other. And the second involution will map P and K to P and K prime. It will take the same point, but it will take the other trajectory, which is the one that you get after elastic reflection at P. So the condition will be that there is this reflection condition between the tangent to one conic and the tangent to the conic K prime. So both involutions again have fixed points. So you have degenerate conics, which are double lines for I. This will not change the point. And conics with vertical tangent at the intersection point for J. So these are so again, we have two involutions on our configuration space with and is with fixed points. So their composition is the Poincaré map of the Boltzmann system. So you start from a point, you follow the Kepler trajectory until you hit the wall, and then you do this. This would be the involution I, and then you reflect the momentum and follow the next trajectory, which would be K prime. It is the involution J. So this is a Poincaré map, and again, so here one has to complexify and compactify. So this has a compactification. So each level set has a compactification, which is a curve of genus 1. And it is smooth, and one can see it's usually smooth, except for special values of the parameters. Okay, so one way to see that is with the following parametrization of x by the value of the Laplace-Rungelet vector and the x1 coordinate x of the point at which you hit the wall. So it is an algebraic set, and so we have these two conditions that one can write down. So I will not go into the details maybe, but from here you see that the first equation, if you look at coordinates a1, a2, and x, the first equation is a rational, it's a quadratic equation, so it's a rational curve, it's isomorphic projective plane, line. And then you have a double cover, which is given by this x, and it has 4 ramification points, so it's a 2-to-1 covering of a rational curve with 4 ramification points, so it is a curve of genus 1, which is the same as an elliptic curve, at least if you fix a point. Okay, so this is how you see that. And the consequence is this Poncelet property of the integrable Boltzmann system. So let's call the non-exceptional if it's smooth. So if we are outside those lines, those curves. So so the theorem will be that if D and E are non-exceptional and are such that you have one periodic orbit, then all orbits are periodic. Moreover, the period is the same for all those orbits. Okay, and then we can write conditions for having a periodic orbit. So the question is, what is the analog of these Euler triangles in the case of the Boltzmann system? So what are the conditions on the integrals of motions, of the values of the integrals of motions d and e, to have a periodic orbit with period n? For instance, n equal to 3, to analog of Euler. And so you can compute it. You can write the equation t cubed p equal to p for some special p. The point at infinity is a good point because it simplifies the calculation. And you get a condition on E and D for which you have this periodic orbit. And so if the integrals of motions are on this algebraic curve, then all orbits are periodic with period 3. And I'm sure you already found a solution of this equation. If not, it is this. D equal to 7/4 and E equal to -5/24 would be a case where you have a negative energy solution. So by the way, so this, works for complex energies and so on. And of course, you can also look at positive energy solutions, which is fine, but then you have to allow for hyperbolas, right? So you can have a particle which goes off to infinity and comes back from infinity from the other sides and hit the wall from the other side. So if you allow for that, it's also worse for positive energy. But here it is an example where you have period 3. So with 2 initial conditions, you get these orbits of period 3. Right, maybe that would be shorter than just a second. Okay. Okay, so now let's discuss a little bit the real locus. So this was kind of general, complex algebraic geometry, but we can ask when do we have real points? So let's take 2 real values of the integrals of motions, and then we have an elliptic curve defined over R, namely given by equations with real coefficients, and the real points are fixed points for an anti-holomorphic involutions of these complex curves. Now, there is a classification of, so maybe one question is, when is this X, D, and E non-empty? And the other question is, how does it look like? So it's an elliptic curve, so it is a group. So what is this group? What is it as a Lie group? And so we have 2 possibilities, right? So a real elliptic curve can have kind of 2 connected components or just 1 connected component. So one is called the unipartite case, when you have only 1 connected components, or the bipartite case, where you have 2 components. And as a Lie group, this elliptic curve is isomorphic to a circle, or to a circle, if it has 2 components, it's a circle times a cyclic group of order 2. Right, and then the question is, how does first of all, for which parameters you have a non-empty level set? And so first of all, we have a symmetry. If d and minus d is the same, oops, sorry. And sorry, I need to move this zoom window, which is always okay. So we can assume that d plus 2e is larger than or equal to 0, and actually, if you compute the angular momentum, this is a case where you have real angular momentum. If you minus d and minus e, you would get imaginary angular momentum. So anyway, so this is the kind of physical region, and then this is non-empty if if either this less than 2 or you have these inequalities here. So I have a little picture to explain that. So this is a parameter space. We have D and E, the energy and this combination of angular momentum and Laplace Runge length vector. And the gray region is the is a region where you have non-zero, non-empty level set. Now these blue lines D equal to 2 and D minus 2, and also this kind of boundary region on the upper left, they are the regions where the elliptic curve becomes singular, so it develops a node or something. And then we have these three connected regions delimited by this singular locus D equal to 2 and D equal to minus 2. So it turns out that all kind of behaviors are possible in these three regions, namely in the region 1, we have just one component of this real elliptic curve. So as a Lie group, we have S1. So after a change of variables, if you like, our dynamical systems becomes simply the translation by a rotation angle alpha. And then in region 2 plus, you have two components. So as a Lie group, you have this S1 cross a cyclic group of order 2, and the Poincaré map of our system is conjugated to a translation of alpha, but then at each step you go from one component to the other. So you add the class of 1 in Z mod 2Z. And in the second, in the region 2 minus, which only has points with positive energy, you have again two components, but this times you stay on each component. The Poincaré map preserves each of the components. Sorry. Okay, so it looks like this Boltzmann system contains all possible behaviors. And also, if you look at the complex situation, then what you are really describing is the moduli space of elliptic curves with two marked points. So each curves of genus 1 with two marked points, and so that moduli space has a compactification, the Lin-Mumford compactification. So the stable compactification, so you can have one nodal points or two nodal points, and so all these kind of all possible moduli appear in this parameter space, and also all kind of stable degenerations appear in this Boltzmann parameter space. So somehow the Boltzmann systems knows about the whole moduli space of genus 1 curve with two marked points. Okay, so now let me discuss. So maybe so here I have no slide for this, but this I wanted also to mention. Right. So there is this question of what happens if we add this. Maybe I should shortly go back to the start. So Boltzmann, so what I described so far is a case where lambda equal to 0 in this potential. And now you can ask what happens if I add the centrifugal term lambda, as which Boltzmann added, and he was clever to do it because right, for lambda equal to 0, this is integrable. Now, if lambda is small, then there is this so-called KAM, Kolmogorov-Arnold-Moser theory, which tells you how to deal with perturbations of integrable systems. So this would be an integrable system, a perturbation of an integrable system. So more precisely, we have an area preserving map, and so we'll consider iteration of these area preserving maps. So Moser has a theorem about that, which applied to the so-called standard map, which tells you that if you perturb such an area preserving map, you perturb, which is as we were explaining, the perturbation of a rotation of a circle by a constant angle, then you still have invariant tori. So you need to have some conditions. The condition is also, so you have a family of so you have, I think in the setting of Moser you have an annulus, which is a union of circles, and on each circle you translate by a fixed amount. So you rotate by a fixed angle, but the angle depends non-trivially on the radius. So this is called an isochronous system. So if you have this anisochronicity condition, then you can show that if you perturb your area preserving map, then you still have invariant circles. You have still a lot of invariant circles. You certainly don't have a chaotic system. This is one instance of this KAM theory. So in other words, at least when lambda is small, you cannot, from what I explained today, you can deduce that this anisochronicity condition is conserved, is fulfilled, because you have some explicit description of this elliptic curve. Basically, it means that the element of the elliptic curve changes if you change the parameters, and this you can verify explicitly. And so this Moser theorem applies. So for small lambda, it is not chaotic. Then you can ask, okay, maybe, so at least in this range, Boltzmann was not right, but maybe for large lambda, it is possible. And Jauslin indeed has some numerical experiments suggesting, but of course in numerics it's hard to judge, suggesting that the system is indeed chaotic for large enough lambda. Okay, so now let me talk about a more general class. So the Poncelet problem and this Boltzmann system turn out to be some kind of special cases of a class of system, or can be recast in a kind of more general class of systems, which are called Quisper-Roberts-Thompson maps, QRT maps. So this is a very simple and very nice classical construction. So you look at biquadratic polynomials in two variables. So it's a polynomial in two variables which is quadratic in both. It has terms u square, uv square, u square, v square, and so on. And so consider the corresponding plane curve given by the zero set of this polynomial. It's again a curve of genus 1, if it is smooth. And so again, we have two involutions here. Namely, we have a curve in the plane, and let's intersect it with vertical lines and horizontal lines. Since we have a quadratic equation, these lines will intersect our curve in 2 points, right? So we have again two involutions. Namely, the first involution will map u and v to u prime and v, where u prime is a second solution of this equation with fixed v, quadratic equation. It has two solutions, and j the same for v. And then you can iterate those involutions. So you start from a point, you go down, point on the curve, you go down along a vertical line until you hit it again, then you go horizontally until you hit, and so on. So you get some nice picture like this. And now, again, you can consider, again, these are kind of inversions. So they're involutions with fixed points, which are the kind of boundary points. So points of tangencies with horizontal and vertical lines. And the composition is a translation of on the elliptic curve. And again, there is a Poncelet property. So the Poncelet problem can be recast in this language in suitable variables, and also the Boltzmann billiard in suitable variables can be rewritten in terms of as a biquadratic curve. So this, now here I draw the composition of horizontal and vertical involutions, and iterate it, and you get a picture like this. Okay, so there are many examples of this. There is a Poncelet, as I mentioned, and then there is some, for instance, the 4-bar link of Darboux. So you consider a quadrilateral with you make it up with wood sides. So the sides of your quadrilaterals don't move, don't change. But what you do is you reflect two sides along the diagonal, and you get a new triangle, quadrilateral. Then you take the other diagonal of the new quadrilateral and do the same thing, and so you iterate, and you can ask whether it has periodic orbits or not. And elliptic billiards. So there is a nice book, by the way, of Dijkstermaat, which is called the Discrete Integrable System, QRT Maps and Elliptic Surfaces, which describe this, and is also an introduction of the algebraic geometry that you need for this kind of problems. Okay, so this is a general class of systems, and now it is useful to use the language of QRT maps to describe the three-dimensional case. Now, the three-dimensional case will be the Boltzmann's table tennis. So you just take a table tennis, and now you have a ball which jumps, and you ask if there are quadratic orbits. Okay, so you consider a motion of a particle in R3 subject to a Newtonian gravitational force with center at the origin and reflecting elastically when it hits the wall, which is now x3 equal to 1. And the center is at the origin, the center of attraction. So now, what are the integrals of motion? So again, you have the energy, which is conserved. And this is still this D, this combination of angular momentum and length vector, Laplace-Runge length vector, is still conserved. And so again, you have this picture that the second focus of the Kepler trajectories moves on a sphere centered at 002, the reflected image of the origin with respect to the wall. So, but here you have a third, you have one more degree of freedom, you have a third conserved quantity, which is the third component of the angular momentum. And this, of course, you know, it's because you have rotations invariance with respect to the vertical axis, the axis perpendicular to the wall. And actually you have an O2, you also have reflections with respect to planes perpendicular to the axis as a symmetry. So you have an O2 symmetry of the problem. There is also time reversal, so there is some discrete stuff, but basically the upshot here is that L3 is a conserved quantity. So you have three integrals of motions. And now it turns out that now the generic non-empty level set of the integrals of motion is a principal O2 bundle. So if there are some bad, or I don't know, values of EDM, but if you take them generically, then the action of O2 is free, and you have a principal O2 bundle. And again, it's over an elliptic curve. So now we have a surface instead of a curve. We have a surface, which is an O2 bundle over an elliptic curve. And this in suitable coordinates, this curve is a biquadratic curve. and the induced Poincaré map. So the O2 symmetry commutes with your map T, the Poincaré map, and so it induces a Poincaré map on C on this base curve, and it's a QRT map in those coordinates. Again, it is as before. It's composition of two involutions, and it's a translation for the elliptic curve. So at least what we have is a priori Poncelet property modulo rotations. So, but we will come to that. Right. So here is an example. Actually, to tell the truth, it's a kind of more very degenerate example where the Poncelet property does not hold. This type of examples also happens in 2 dimensions. It's when you are, so another type of periodic orbits is when you, for the billiard, is when you take an elliptic curve with a nodal point, so a singular elliptic curve, and you go to this nodal point, then you don't move from there, and you have period 1, or I don't know, period, you just have a fixed point. And so this is a similar example, and now you have a fixed point, but up to rotation. So what happens is that, and this is easy to construct, these special solutions, where it's like a merry-go-round. You jump over a circle and go back. So the parameters are chosen suitably. You have all the collisions are on a circle of radius 1, centered above the center of attraction. So this is a degenerate case, actually. And so here is some result in work in progress with Misha Feigin. So we can complexify this. We complexify first the story, and there one has to consider a partial compactification of this complexification, so that it's preserved by the Poincaré map, the complexification of the Poincaré map. And so then it extends to a homomorphism of this complex surface now, x, e, d, m, with these 3 parameters, which are the values of the integrals of motion. And so for generic levels EDM, this surface is smooth, and it's a principal bundle over a smooth elliptic curve. And the structural group is a complexification of O2, which is C star and Z mod 2. So it has 2 components, right? So this surface X has 2 components. Because it's a principal bundle and the structure group is not connected. So I mean, maybe it doesn't follow, but it is a fact that we have these 2 components. Now it turns out that the Poincaré property holds for generic EDM. So either all orbits are periodic with the same period, or none is. So more precisely, how does this look like? So we have, first of all, we have a family of such principal bundles. So for each, so we have a parameter space, which is a fine 3-dimensional space, coordinates EDM, the values of the integrals of motion. And then for each value of the DM, we have this fiber, which itself is fiber, is a principal bundle for that group. It has 2 components. And now now the induced automorphism on the elliptic curve is of finite order. So now on this parameter space, you have, first of all, 3-dimensional parameter space. First of all, you have surfaces Sn, and on those surfaces, the induced map on the base curve has finite order n.
Excuse me.
Yes.
The Poincaré property or the Poncelet property?
Sorted. Yes. Poncelet property, not Poincaré. Thank you very much. Poncelet property. Yes. So the induced automorphism is of finite order n. So what does it mean? It means that if the parameters are on the surface Sn and you start, then you will jump around and come back to the same point up to rotation or of SO2 rotation. And now you have an additional condition if you want periodic orbit, that this rotation is actually the identity. Okay, so namely in that case, if the induced map on the base curve is of finite order, then the nth of order n, then the nth iterate of the Poincaré map is Gn. Gn is a group element, in O2C group element, actually in SO2, it turns out, for all x. And it turns out that this is independent of x, so you have a fixed element of SO2 which acts. And now you have a second condition which they ask you for this element to be the identity. And so on these surfaces Sn, you have some curves where this Gn is of finite order more generally. So then all orbits are periodic of period n times m if the parameters lie on a curve, Cnm of the parameter space, on which Gn has finite order m. And right. So here I have the simplest example I could find with negative energy and real, right, is when n is equal to 3 and m equal to 3. So I don't know if it is visible, but so this has order 9, and so after 3 jumps you come back to a point which is obtained from the starting point by some rotation of an angle 2 pi over 3. And so if you iterate 9 times, you go back to the starting point. Okay, so of course you can try this at home if you like, but you'll need to buy yourself a larger a rather large tennis table. The tennis table which I draw here is has a side length of 7 times, I think, the distance to the center, so it is 7 times the radius of the Earth or so. And then you can try this at home. Okay, thank you for your attention.
Thank you for the very nice talk. It was very, very interesting. Any questions, comments? Please go ahead and unmute yourself.
Yes, this is
Yes.
a silly question from curiosity. So going back to billiard, is the case with straight line the only case you have integrability? Like if you have like 2 straight lines crossed with right angle, and then don't you have something like different conservation or?
I think what I know is that maybe 2 things I know, which is not much. So one thing is that if you take the second line to be perpendicular to the first and going through the center, then you still have an integrable system. But this is rather simple. And the other thing is that there is there are some paper of I'm not sure I can pronounce his name correctly, Liao, who consider some more general situations where you have circles instead of lines and various kind of projections and variants of this construction. So straight lines is not the only possibility, and so there are a few other.
So in this extension, they have integrability, even though it's something more complicated.
Right. There are some, but special examples, right?
Okay. Thank you.
So concerning generalization, so how does it go if you try to do higher dimensions?
Yeah, right. So I think so. Like in this case, for instance, what you can show is that if you try to do n dimensions, then actually the motion will always happen in a three-dimensional subspace. So you will not have a true generalization.
Okay, so the table tennis is the most general.
Yeah.
Well, what about another generalization? If you consider generic potential, can you say something interesting?
No.
I mean,
So I mean, it's rare to have this.
So
this additional integral of motion.
And this centrifugal force, I mean, the potential, the Coulomb plus centrifugal is still exactly solvable.
Yes.
So this was probably the motivation of Boltzmann to consider. So so it is still somewhat special.
Right. So yeah, that's true. But so of course the system is exactly solvable, but the if you introduce the wall, it is a little tricky, because what happens is that so the typical trajectories are this. Maybe I can try to use my blackboard. I don't know if you see the
yes, we can see this.
I should not stand in front, probably. So this is a kind of typical form of those trajectories if you have a centrifugal force. And now you can imagine that it's a complicated story to find the next point of intersection, because you vary a little bit. So the Poincaré map is not continuous, for instance. You vary a little bit, you might meet the wall on this meander, that on the earlier meander, right? So of course the form of this trajectory is known, but the map between one hitting point and the next is complicated to describe.
Another question: what is the role of complex numbers, of complex analysis here, or complex geometry? So suppose, I mean, we don't care about real numbers. Does it help, or does it clarify the picture?
Yeah, it does clarify, because sometimes you don't see, you don't. So I think you can, in the end, you can formulate everything in real terms, but then you have to say, I should assume that it's not empty, and so on. And also, for instance, in this Griffith's argument, you need to check that your involutions have fixed points to classify them. But typically the fixed points are in the complex domain, even if you have a real curve. So to describe the geometry, it's better to go to the complex plane.
Can I ask a question quickly?
Yes.
I was wondering if you can see any traces of a geodesic flow somehow hiding behind all of this story. I'm thinking if you didn't, well, if you reflect the trajectory after a bounce, you can find a smooth trajectory. And perhaps you can think of this as being the geodesic for some effective metric that your problem gives you. And then the problem of ergodicity or chaoticity of the flow would become a question about the metric, for example, the curvature, the sectional curvature of this metric.
Let me understand what you mean. But we have a discrete time system, right? So
yes, but you can think of this as coming from some flow in a larger space, and then you're just looking at the Poincare map for a slice.
For a slice, right? Yes, yes. Yeah, I don't know. I don't know. Right. Yeah. Right. So we call it Poincare map. But so I think what you mean is that maybe one should smooth out those reflections, right? Map it to another system, and instead of having a reflection, we are recording the time at which we meet some hypersurface or something like this. Yes, that's a good proposal. I don't know how to do it.
Okay, any other questions? Okay, I think we are through. So let me thank Giovanni again.
Welcome.
Thank you very much.